this drops by, this has to increase by, since this is a fixed current source here. Okay, so remember what happened when you raised in a diff pair. If you raise the voltage, we'll look at an NPN input diff pair. If you raise the voltage, the current through that branch increased. Let's see, if I raised V2, this current drops and the current through this branch increases. That's exactly what happened with the telescopic. When I raised one of the input, the current through that side of the branch increased. Okay, well, let's see if this behaves like the other side of the diff pair. Okay, we said if this decreases by some current, delta I, this has to increase by some current, delta I, because these two have to sum to your I ref. Okay, so this is I ref plus delta I. This is going into M9. If this is supplying I ref over to plus delta I, so if this is supplying I ref over to plus delta I, now this side has to conduct a little bit less. It has to conduct I ref over to minus delta I. So this will sum to I ref again. Okay, so let's see. When we had a diff pair, when I dropped the current, so that's that voltage. So what we've done is we've raised V2 and dropped V1. We saw when we raised V2, the current through this branch actually increased. So let's say I dropped V1. Now the current through here increases and the current through here decreases. Okay, so that's exactly how, and by the same current amount, the diff pair steered current. Okay, this goes up, this current goes up, this goes down, this current went down. And you can practice going the other way, saying, what if, oh, okay, what if V2 went down? What happens to this current? Okay, if V2 goes down, the current increases. If the current through this branch increases, the current through this branch has to decrease because it has to sum back to I ref again. And you get the exact same behavior through this circuit. The exact same behavior as you got with the telescopic, except now you have one less transistor. So here's the big question. Yeah, you got a little better V out swing because you got rid of a transistor. So if there's something good that happens, you can almost bet there's going to be something bad that happens. And that is the gain drops. And so let's think about why that could be. Remember, you've got GM RO. GM is actually, it's this whole complicated thing here, but it's still the GM of your input transistor. Okay. So the GM doesn't change, so it has to be the R out that drops the gain. Now looking up, wow, that's cascoded. That's a lot. That's a high resistance. Okay, so that's your RO squared. Your GM6 times RO squared. Okay, so if the top is really high impedance, then maybe it's looking down. If you look down, okay, you see M8 and you see M10. But if you notice, now you've got this entire path in parallel with M10. So the current has two choices. It can go down through M10 or it can go out this way. And because it has two paths, it reduces your R out. And if you look at the change in gain, you can see that with the telescopic, you have a nice gain. For the example, I have a couple of graphs of cascoded. You have an R out of 2.4 mega ohms, and over here you have 1.4 mega ohms. And that translates into, since they both have the same GM, that translates into a difference in gain of quite a bit. Okay. So I'll summarize here. I don't think I've been talking for a whole hour. Maybe I have. But I'll summarize here by saying that ways to increase your gain. Okay, first of all, if you have a common emitter, active load. Okay, that's the first step. Differential pair doesn't increase your gain, but it makes it much easier to bias. Plus, it's pretty robust against noise. Okay, if you want to make your differential pair a higher gain, again, active load, or with either a single-ended input, single-ended output common emitter or a diff pair, you can cascode them. And you have to do that to the top half and the bottom half. The top have to be P devices and the bottom has to be N devices. And when you cascode, you always want the input on the outermost transistor. Okay, so that gives you an added gain of small RO. The gain gets multiplied by that factor, which is quite a lot. And then if you really want more gain, now what you can do is you can gain boost your cascoded amplifier. That gives you an additional gain of, your gain gets multiplied by whatever the gain of that little amplifier is that you use at the base of your second transistor. Okay, and then the one of the drawbacks of the telescopic is that it has that tail current source, which means you have at least 5 transistors stacked. To get rid of one, you can do folded cascode. That gives you a little more leeway. You can have a wider output swing, but what it costs you is in gain. Okay. I think a number of these topics are about things that I don't want to talk about with lab, but let's look at, let's do one more thing here. The final step of the lab is going to be to use feedback, and I hope everyone's seen this at some point. We'll go through it in class again. But when you add feedback, you'd say, okay, well, how do we do that with the amplifiers we've seen so far? And here's a fully differential op amp. We should do a simpler one. Okay, let's say you had that, your R feedback and your RN. If you have a diff pair, you have a plus input and a minus input. And I think, let's see, what would that be? Just that. I think that right there, without this RF and without this source right here, I think that is that. Okay, so you already, with a diff pair, you already have pretty good gain. You have a differential input, so you can feed back to the, this is back to the positive terminal. Yeah, that's right, okay. The only reason that a diff pair isn't a perfect op amp is because it has a high R out. Okay. So this diff pair over here, it already allows you to do any of those op amp configurations that you learned about in 211 or these other classes. Okay. So that was a quick spin through all your options for 348. That's a quick spin through all your options for upping your gain stage. And for 308, I'll go back and go over these pretty quick, just so if you do have questions, you can ask them. Okay. And plus, there's going to be a couple of MOSFET topics that I want to touch on before we finish this topic. Okay. Well, thank you very much.